Hey there, chemists. Welcome to our very last unit in Regents level chemistry. Today I'm going to be introducing to you guys the nuclear chemistry unit, one of my favorite units of the year. To introduce this, I always like to use this really short clip from Harry Potter and the Philosopher or Sorcerer's Stone. So let's go ahead and take a look.
I had you looking in the wrong section. How could I be so stupid? I checked this out weeks ago for a bit of light reading.
This is light?
Of course, here it is. Nicholas Flamel is the only known maker of the Philosopher's Stone.
What?
Honestly, don't you two read? The Philosopher's Stone is a legendary substance with astonishing powers. It will transform any metal into pure gold and produces the elixir of life, which will make the drinker immortal.
Immortal?
It means you'll never die.
Okay, and we're just going to cut it off there because what I like about this clip is that it introduces this idea of a much earlier form of chemistry called alchemy. And more specifically, it introduces this idea that alchemists were really interested in finding kind of a couple of things, right? Immortality, but also the ability to kind of convert any substance into gold. And so, I always think this is really interesting. If you look into the history of alchemy and kind of this idea of them trying to transfer or create gold out of anything, you can actually find a lot of really crazy stories of what they used to do. And one of these examples that I like to use is what is gold colored and really easy to get your hands on. They actually used to think that you could boil down urine to try to create gold, right? Golden colored, and then they can make gold from it. Okay, obviously didn't work, but they did accidentally discover phosphorus during that experiment. Anywho, we'll talk a little bit about why this idea is so far-fetched in just a moment, but let's go ahead and dig right into our notes sheet for today. So as a quick review, it's been a really long time at this point since we've kind of focused on and talked about the different subatomic particles that are found in each atom and kind of just reviewing what we know about that. So let's go ahead and take a moment and calculate protons, neutrons, and electrons in these four atoms, okay? Now, again, you can use your reference table to find all this information, okay? So for carbon, right, in order to help us figure out the number of protons, neutrons, and electrons, we can go ahead and use our element symbol. So our protons is the same thing as our atomic number. Okay, and so for carbon, that's going to be 6. Okay, for neutrons, in order to determine neutrons, we're going to use the mass minus the number of protons. So carbon 12, remember, this is the mass number. Okay, and so we end up getting a mass number of 12, so this is going to be 6. And electrons, remember, atoms are electrically neutral. And so for our number of electrons, it's going to be equal to our number of protons. And therefore, that's going to give us 6. Okay. Carbon 13, still carbon. So therefore, because it's still carbon, we're still going to have 6 protons. However, our mass number in this case is now 13, and therefore we have 1 additional neutron, so 7 for our neutrons. And again, it is electrically neutral still, so it's still going to have 6 electrons. Now, nitrogen 14, looking for the atomic number. Nitrogen is N. N is element number 7. So we have 7 protons. For our mass number, that's going to be 14, therefore creating 7 neutrons. And again, it's electrically neutral and therefore 7 electrons. Take a moment and pause the video now and see if you can use the symbol provided for you below for helium to help you figure out the number of protons, neutrons, and electrons. Go ahead and pause now. Okay, welcome back. So for our number of protons, now this is written in isotopic notation. It's been a while since we've thought about that word, I'm sure. But what it did is it provides you actually with the mass and the number of protons or the atomic number right there in the symbol. So our number of protons or our atomic number is listed in the bottom. That's going to be 2. And our top number is our mass number. okay? And therefore it's 4, so I have 2 neutrons. It's electrically neutral, and therefore you have 2 electrons. Now, again, what makes carbon considered carbon? Well, to take a deeper look at this picture, we can actually go ahead and just look at the fact that we have carbon 12 and carbon 13. And the thing that they have in common with one another is their number of protons. So the identifying feature of an element is going to be the number of protons. So our number of protons defines the atom. Okay? If the number of electrons in an atom varies, it is called. So think about electrons. We keep talking about how electrically neutral an atom is, and so therefore we have equal protons, equal electrons. But if we have varying numbers of protons and electrons, we now have charged particles, right? This makes a charged particle. And a charged particle, if you think back, is called an ion, right? And we have either positive or negatively charged, depending on if you gain or lose electrons. And then lastly, if the number of neutrons varies, like we see here from 6 to 7, they're both carbon. This is a throwback. This is called isotopes. Okay, and isotopes have a different mass and therefore, or a different number of neutrons and therefore a different mass as well. Now, let's go ahead and take a look at this quick reading to kind of introduce us into kind of the underlying kind of key idea of nuclear chemistry. So the radioisotope molybdenum 99 naturally decays. So molybdenum 99 naturally decays to produce metastable isotope technetium 99. So we actually have 99MO becoming just on its own 99TC, which is used in medical diagnoses. A doctor can obtain images of organs and bones by injecting a patient with a solution of technetium 99. So based on kind of our idea of chemistry and what we know, what's wrong with this idea? Well, I want to point out here that we have this substance just naturally going from one atom to another atom. Now, 99 molybdenum has an atomic number MO. Okay, molybdenum has the atomic number, I'm just trying to scan, of 42. And it just on its own becomes technetium, which has an atomic number of 43. So we have one substance magically becoming another substance. We have one substance not just changing electrons, not just changing neutrons, but changing protons. And that's kind of the basis here of nuclear chemistry. We have all these substances that are seemingly magically becoming other atoms. So this idea of our number of protons changing is called transmutation. And this is going to be defined as a reaction in which one element is converted into another by loss or gain of subatomic particles. And I don't want to just say that we're changing protons because it's not just quite that simple. We're going to tomorrow break down exactly what is happening in each different type of transmutation, and it does get a little more complex. But so what does this look like? Here's another example for you just so you have one on your sheet. Okay, we have 226Ra that naturally becomes 222Rn. And in the process, it also gives off a 4,2 helium atom. So you might be thinking to yourself, well, are all the particles around me just constantly changing into different particles? And the answer is kind of yes, that is happening all around us, but not every particle is going to undergo transmutation. So how do we determine which particles are going to undergo transmutation? So just as, again, a quick review, which subatomic particles are specifically found in the nucleus of an atom? So again, if you think back to our history of the atom unit, in the nucleus, we have protons and neutrons. Okay, and so let's go ahead and talk about two very different atoms here, oxygen and polonium, and let's go ahead and calculate their protons and neutrons. So oxygen is going to be element number 8 on your periodic table, just for reference, element number 8, and polonium is going to be element number 84, just for your own references. Okay, so for number of protons, okay, we have here 8, because its atomic number is 8. And for number of neutrons, we need to take that mass number, which on our periodic table is just about 16, subtract our number of protons, 8, to give us 8 neutrons. So we have 8 protons, 8 neutrons. For polonium, again, we have for number of protons, its atomic number is 84, and therefore 84. For the number of neutrons, this is going to be a little bit different. We have 209 minus 84. Okay, so 209 minus 84. So let me just go ahead and punch that into my calculator, and we get 125 neutrons. Now, I've went ahead here and I've gone and placed some labels here for radioactive versus stable. Oxygen is an extremely stable atom, okay? So if you're super stable like oxygen, you're not going to just undergo transmutation. However, polonium is extremely radioactive, and it's radioactive and therefore will undergo transmutation. So just looking at these two pieces of information here, what determines if an atom is considered stable? Well, based on the information that we've been provided here, notice how oxygen has really equal or very, very close in number protons and neutrons, where polonium has very different protons and neutrons, okay? And so what's going to determine stability is if the proton to neutron ratio is close to 1:1, then that means that the atom is going to be stable. So the closer you are to having equal protons and equal neutrons, the more likely we are to be stable. Now, I want to point out that I've also included this diagram here to the left, and this also represents stability. This black line that you can see here on the graph, okay, which I just sort of did a terrible job of drawing, is called the belt of stability. Okay, the belt of stability. And so the belt of stability, notice how it measures that 1:1 ratio. As you can see, we get more and more different types of decay the further we are from that belt of stability. And if you look at your periodic table, the further that you get down, the bigger the atom. Notice how they're becoming more and more unstable. All right, and so these unstable atoms are referred to as radioisotopes. Okay, so our unstable atoms are referred to as radioisotopes. So these are going to be atoms with unstable nuclei, and you're going to be able to find all of these on reference table N. And I'm not going to focus too heavily on reference table N for today. We're going to kind of hold out for that tomorrow, but just knowing that we can have a kind of list of these different unstable isotopes provided for us. Now, radioisotopes look to achieve stability by producing radiation or decay. I guess this got photocopied in kind of the wrong space. So I'm going to write directly over it. I do apologize for that. That's going to look a little annoying. There are 4 main types of decay here. Okay, the first is going to be alpha decay. Alpha decay. And I'm going to fix this for your notes sheet. So, just bear with me how mine looks for here. Okay, so alpha decay. Our second type is beta decay, let me write this maybe in a different color. Maybe if I write it here in pink, beta decay. Okay, we also have beta positive. Okay, and we have gamma. And let's go ahead and fill in a little bit of information about each of these. Our alpha decay has a mass of 4 AMU. Our beta decay has a mass of 0. Our beta positive has a mass of 0, and our gamma has a mass of 0. Alpha decay's charge is a +2. Beta decay's charge is a -1. Beta positive is going to be a +1, and gamma is a 0. Okay, we have symbols that we can use to represent these different types of decay. So alpha, excuse my very poor alpha symbol, but alpha for 2, the mass number on top, charge number on the bottom. Beta decay is going to be 0 -1 with a beta symbol that I'm really terrible at also drawing. Okay, now I want you to think to yourself too, beta 0, 1, -1, start thinking, what other thing do we know that has a mass of 0 and a charge of -1? Hold that thought. All right, beta positive is 0 + 1 beta, and gamma is going to be 0, 0 gamma symbol. Now, again, each of these can actually be defined as something else. So our alpha decay has a mass of 4 and a charge of +2, which is the same thing as 4,2 helium. So this can sometimes be referred to as helium decay as well. Beta decay, 0 -1. What do we know that has a mass of 0 and a mass of 0 and a charge of -1? Okay, and that's going to be an electron. So we can also symbolize this as 0 -1 electron. Positrons are really interesting. They are the antimatter of the electron, and so we can also just kind of symbolize this as 0 + 1 e. And gamma is just is what it is on its own. Now, all of this information is provided for you in reference table O. None of this is something that you have to memorize. Okay. All right. Really quickly, I know this video is a little long. I do apologize. I want to talk to you guys about the strength of these different decay modes, right? We've heard of things being radioactive. At what point does it become super dangerous? Which ones should we be most concerned about? And from our diagram here, what we can see is different amounts of penetrating power. And the piece of information that we're missing is which arrow represents which. Our top arrow is alpha. Our next arrow is both betas. And our bottom arrow is gamma. Notice how alpha can't even go through a piece of paper, okay? Whereas beta can make it through a piece of paper, but not a sheet of aluminum. And gamma, really strong radiation, can make it all the way even through a thicker sheet of lead. And so gamma is the strongest form of radiation, okay, because it is just energy. It carries no mass whatsoever, it carries no charge, it's literally just straight energy. So our weakest form of radiation to our strongest form of radiation is going to be alpha, beta, both positive and negative, and gamma. All right, I'm going to pause here. I know there's more here. There's not much. I'm going to tie it into tomorrow's lesson just for interest of time. Thank you guys so much. You guys have a great rest of your day, and I'll see you guys tomorrow.